In this video, I want to show you a really cool way to solve a constrained optimization problem, which is a problem where you're trying to find the minimum or the maximum of a function, like j of x, and it's subject to a constraint c of x equals 0. And the solution involves this equation down here, where the inner portion is called the Lagrangian, and lambda is called the Lagrange multiplier. So what is this equation doing, and how does it help us solve constrained optimization? Well, it's actually rather intuitive and kind of amazing, so I hope you stick around for this really quick explanation. I'm Brian, and welcome to a MATLAB Tech Talk. Let's look at an optimization problem with an objective function j of x equals x squared, which is plotted over here on this graph. And the question is, what value of x produces the minimum j? And obviously, looking at this graph, it's x equals 0. But what we want to know is, how can we determine this mathematically? Well, one thing we can notice is that the slope of the function is non-zero everywhere, except at the minimum point where it's flat. In fact, minimum and maximum points must exist where the slope is flat, because if the function was increasing or decreasing still, well, then that point wouldn't be the most extreme. And we can tell if a flat point is a minimum if the rate of change of the slope is positive, or if everything is curving up and away from it. And it's a maximum point if everything is curving down. Therefore, for j equals x squared, we can solve for where the slope is 0 by taking the derivative of the function with respect to x, and then just setting that derivative equal to 0. And then we can determine that the rate of change of the slope is positive by just looking at the second derivative at this point. Now, similarly, we can show that x equals 0 is a maximum point for j equals negative x squared, since the second derivative is negative, and therefore we can deduce that the output is curving down from this one point x equals 0. And then finally, we can show that the flat part of j equals x cubed is neither a maximum or a minimum point, since the second derivative is 0 at this point. It's neither positive or negative. And the idea of looking at the slope can be expanded to higher order functions as well. For example, this function, j equals x1 squared plus x2 squared. We can look at this and once again pretty easily see that the minimum j occurs when x1 and x2 are both 0. Now, to find this point, we once again look at where the derivative is 0, or more precisely, where the gradient is 0. The gradient of j of x is the partial derivative of the function with respect to both x1 and x2. And when we do this, we get the vector 2x1 and 2x2. So really, the gradient returns a vector field that denotes the direction and the magnitude of the steepest slope for every possible x combination. And for our bowl-shaped function, the gradient looks like this. There is 0 slope at the very bottom of the bowl, and then it gradually becomes steeper as we move towards the edge in all directions. And this is the basis of all optimization problems. We set up an objective function and then solve for, or in a lot of cases, we search for the locations of 0 gradient. And I say search for because often objective functions aren't as straightforward as this, and we have to hunt for the optimal point with gradient descent type algorithms. And these are algorithms that find the optimal point numerically with an iterative approach by descending the gradient. That is, it's going in the opposite direction of the arrows until you reach a stationary point. All right, this is probably a good time to bring up the issue of local and global minima. If we're looking for stationary points using gradient descent, then where that algorithm starts its search becomes really important. If there are multiple basins, then a gradient descent algorithm will get stuck in a local minimum if the starting state is within that basin of attraction. And there's different methods for addressing this, including just picking many different starting points and then running gradient descent on each one and seeing where they all end up. But what's really nice about the analytical approach of taking the gradient of the function is that each of the stationary points can be identified mathematically by setting the gradient to 0 and solving for x. Here, we have 3 stationary points corresponding to the local minimum, the global minimum, and the local maximum that occurs between them. So now we can just check the value of the objective function at each of these stationary points and then pick the lowest one to find that global minimum. All right, so that's the unconstrained optimization. That's where we're free to choose any value that minimizes our function. But this video is on constrained optimization. And with constrained optimization, the objective function is subject to an additional constraint. In this case, let's say that the constraint is x1 plus x2 plus 3 must equal 0. So that means that we can only choose combinations of x1 and x2 that lie along this line. And now if I raise this line up, this means that we're really looking for the minimum value along this intersecting parabola. So now how do we find this location? Well, let's change the surface plot into a contour plot. And so now we can imagine that we're hiking along this black line on a surface that has this contour. And so at the beginning, you're hiking down pretty steeply as you cross the contour lines quickly, and then it gradually gets less steep. And then right here, right when your path is exactly tangent to a contour line, you've reached the lowest point, and then you start heading back up again. So the lowest point is where the path is parallel to the contour. Or another way of putting it, it's where the path is perpendicular to the gradient. And this makes sense, right? I mean, if the gradient is the direction of the steepest travel, and you're walking perpendicularly to that, then you're not going up or down right at that point. Your path is flat. Now, to calculate this point, we can do something clever. We can compare the gradient of the objective function with the gradient of the constraint. And if the gradients, or the directions of the steepest slope, for the two functions are parallel, then this is a stationary point. And therefore, it's either a maximum, a minimum, or some kind of a saddle point like we had with x cubed. So the gradient of the constraint is the partial derivative with respect to both x1 and x2, which it turns out is just 1 for both directions. And if I plot that vector field on our graph, we get these arrows that are all perpendicular to the black line. And notice that at the minimum point, the gradient of j is parallel to the gradient of c. Now, they are pointing in different directions, but they are parallel. So to make them equivalent, we can simply multiply the constraint by a constant, lambda. And choosing different lambdas is essentially scaling the gradient, either positively or negatively like I'm showing here. And the idea is that we want to find the Lagrange multiplier that makes the two gradients equal right at this point where they are parallel. Okay, so now let me rearrange this equation, and what we're left with is the equation that we started with. Now you're going to notice that if you do this rearranging yourself, it should be a minus lambda c, but to make the equation look better, we just roll that negative into the constant lambda, which can be positive or negative. All right, so the solution to the problem exists where the gradient of the Lagrangian equals 0. And again, this doesn't tell us if we're at a maximum, a minimum, or a saddle point. We know that we need some form of a second derivative to determine that. And generally speaking, that second derivative comes in the form of a bordered Hessian matrix. And I'm not going to cover this here since I just wanted to talk about the Lagrangian itself. And also in our problem, we know that the point is a minimum due to our understanding of the functions. But I did leave some good references for it down below. All right, so now that we understand why the Lagrangian is important, let's use it to solve the constrained optimization problem. Our Lagrangian is x1 squared plus x2 squared plus lambda times x1 plus x2 plus 3. And the gradient gives us these three equations, which we can use to solve for the three unknowns by just setting each of the equations to 0. And we find that the optimal point is at minus 1.5 and minus 1.5. And the Lagrange multiplier has a value of 3. And how cool is that? I mean, it's just such a simple idea that we can find minima and maxima of constrained optimization problems just by looking at where the gradients of the two functions are parallel. All right, so now before I wrap up this video, I want to show you how we can actually solve this example in MATLAB, since more often than not, you're not going to be solving it by hand. I have this live script that uses the well-named function optimProblem to solve our optimization problem. And here I've defined the objective function x1 squared plus x2 squared, and then the constraint x1 plus x2 plus 3 equals 0. The function solve solves the problem, and it returns several different outputs. And when it runs, I'm displaying the optimal point x and the Lagrange multiplier lambda. And over here, we see that x is minus 1.5 and minus 1.5, and lambda is 3, just as we calculated. All right, so that's where I'm going to leave this video. Hopefully you have a better understanding of how the Lagrangian plays a role in constrained optimization problems and what the Lagrange multiplier is actually doing. And I've left links below to several different resources and MATLAB examples if you want to learn more. Also, you can find all of the Tech Talk videos across many different topics nicely organized at mathworks.com. And if you like this video, then you might be interested to learn about a popular type of constrained optimization that we use for control problems called the linear quadratic regulator. All right, thanks for watching, and I'll see you next time.